Hi there, everybody. It is time for another Chem Complete episode for Organic Chemistry 2, and we are continuing with aldehydes and ketones today. And today's lesson is going to be primarily a review. There will be one or two new reactions, but we want to take a look at how to create aldehydes and ketones before we get too far down the road of what aldehydes and ketones can actually undergo in terms of reactions. So let's take a look at how to create aldehydes and ketones. There's going to be several different sources of creating aldehydes and ketones. Many of these should be familiar. Some of them are going to be new, and so you're going to want to take some time to sort of soak that in and add those to your list of potential reagents and other items that could be used to create aldehydes or ketones. So, to get started, and a lot of these we're going to group together as you can create aldehydes and ketones this way, but I'll differentiate it. One of the easiest ways to create aldehydes and ketones is to oxidize an alcohol. And this was something that we looked at back when we dealt with the alcohol chapter. So if I take an alcohol, a primary alcohol, we'll use ethanol for example, and I would like to turn this into an aldehyde, I need to use a weak oxidation in order to accomplish this. And what I will get is the corresponding aldehyde. Now remember, when we talked about this beforehand, you can go back and look at the video if you don't remember it. When we talked about weak oxidation, a strong oxidation gives a carboxylic acid when we're dealing with primary alcohols. This weak oxidation gives an aldehyde, and because we're in the aldehyde and ketone chapter, we're interested in the weak oxidation. There's two potential reagents you could use here. One of them we've already discussed in detail in a previous lecture, which is PCC. PCC is a weak oxidizing agent. There is another one referred to as the Des-Martin reagent. It's really Des-Martin periiodine, and it is abbreviated DMP. So PCC or DMP, which you sometimes may see written out as Des-Martin oxidation over the arrow, either of these are acceptable sources to create aldehydes from primary alcohols. Now, in terms of a ketone, we need a secondary alcohol. And with the secondary alcohol, and while I'm drawing this out, just remember tertiary alcohols can never oxidize. So they will never undergo any sort of oxidation because you would violate the valence rules for carbon. So here I can use weak or strong, so you can pick out any of them. We saw a lot of the strong ones in the previous lecture dealing with alcohols. So these weak ones up here would also work. The strong ones that would work, and these cannot be used with the primary, you'll get the carboxylic acid. These are some examples of some of the strong oxidizing agents that could be used. Okay, we also include acid after each of these in the workup. But any of these would be acceptable to take the secondary alcohol over to a ketone. Right, so this one should be somewhat familiar. We're used to seeing alcohols that can be oxidized up into aldehydes or ketones. And so that's really the first one. Now, the second one is another form of oxidation that we have not seen in quite a while. And this form of oxidation is ozonolysis. And when we deal with the ozone oxidation, we're dealing with O3, the reagent O3. So what we need when we're doing the ozone oxidation, if you remember, we had to have some sort of a double bond. So to start with, let's take a look here. If I have a carbon-carbon double bond, these would each have hydrogens associated with them. And then let's do a simple example like this. If I take this alkene, which is one of the primary organic ingredients I need here, if I take an alkene functional group and I expose it to number 1 some ozone, which is why we refer to this as ozonalysis, this oxidation process. And number 2, you may not remember, but we follow this up with a metal, so we often use zinc and some sort of acid. So you may see HCl, you may see acetic acid, you may see all sorts of acid, but some acidic source along with that metal is going to come by and cleave this double bond and place double bond oxygens in place of the alkene. And so what I would end up with in this case is 2 equivalents of this aldehyde right here. Now this can also be used for ketones if I have a higher substitution pattern around the alkene. So doing a somewhat similar example, but we're going to change this bottom one to a CH3 here, and then we'll change the top to, we'll keep the H there because this will give us a mixture, right? And let's do, we'll expand this. We'll do this. So if I do the same ozonalysis, O3 followed by zinc and acid, if I do the ozonalysis here, take a look right here, I'm going to end up with a ketone on the left. This portion right here is going to form a ketone, and this portion right here, because I have the H there, will form an aldehyde. So what I would end up with in this case would be CH3, C double bond O, CH3, so I'd get acetone. And then the other thing that I would get would be the propanol. And that would be, yeah, I can draw it this way. C double bond O, the H, and then I would have a CH2 and a CH3. So ketones are possible if I find the higher substitution pattern around the double bond. Keep in mind that while we're doing this, you can also accomplish this with a ring. Now when you cleave the ring, right, so if I have this here, a lot of students forget there's an implied hydrogen down here. When I cleave this ring, doing the same methodology, this ring is going to open up into a single chained product that I would come away with. So I would split here. It's a good idea to count your carbons. So what I like to do here is I like to say, and this is not for naming, just for keeping track, 1, 2 at this source right here, 3, 4, 5, 6, and then carbon 7 has the hydrogen there that we're looking at. So if I were to write this out, just write it out sequentially. Start with number 1 and say this is CH3. Number 2 is a part of the double bond, so that becomes a carbonyl. And then number 3, right? 4, 5, these are all CH2s, 6. And then when I get to 7, 7 was also involved in this alkene, and so there's an aldehyde. So again, I have a ketone and an aldehyde that comes out of this. So what we really did, these two guys right here, actually let me do it from below. These guys were attached, and they were split open using the ozonalysis oxidation technique. So that was learned back in the alkene chapter in Organic Chemistry 1, but a very important reaction when we are getting ready to take a look at creating aldehydes and ketones. So something that's a little bit new that we haven't really taken a look at yet, because it doesn't involve alcohols, is that you can take an ester, which is another type of carboxyl group, and you can do a selective reduction on this ester. Now we have seen reductions where basically NABH4 could do the aldehyde and ketone reductions. However, stronger reagents, LAH, lithium aluminum hydride, was needed to do the carboxylic acids and the esters. We actually can do a weak reagent with the ester that will do a partial reduction. Okay, so this is going to be a partial reduction. So what do we normally reduce to? We normally reduce to alcohols when we go all the way down. But we can stop and we can reduce to an aldehyde. And this is a new concept, to take a ester and reduce it down partway to an aldehyde, but not all the way down to an alcohol. And this is accomplished with a compound that's got a pretty long name. It is referred to as diisobutylaluminum hydride. So we've seen the hydride, sodium borohydride, lithium aluminum hydride. This is another hydride. We use it for reduction. You have to use pretty cold temperatures, and we can abbreviate the diisobutylaluminum hydride, and this is the way you're normally going to find it in most textbooks and what your teacher will probably use. They're going to say diiso, so you'll have the di part there, and then the butyl ammonium will be Ba, and then hydride. So DIBAH. You'll hear a lot of instructors say DIBAH this, DIBAH that. DIBAH is a selective reduction of an ester to an aldehyde. Very useful technique. This needs to be done. It's a lot of times there's a solvent that's somewhat neutral like toluene, but more important than that is that this usually occurs at minus 78 degrees Celsius. You might see minus 80 degrees Celsius, but very cold temperatures in order to slow down the reduction process. We basically want to slow it down, and so we use very cold reactions. And I mentioned toluene as a solvent because when you do dry ice with toluene, that mixture comes to about minus 78 degrees Celsius. So that tends to be a very common setup for your DIBAH reagent in order to create your aldehyde. And this gives pretty useful yields of aldehydes. It's pretty decent. So that is another important reaction in terms of how we can create aldehydes specifically. That one is not for ketones. And then the final one that I would really mention to you guys, and this also comes back from Organic Chemistry 1, is what if we have alkynes? And remember, alkynes are triple bonds. So let's make a semi-decent sized reagent here. And I'm going to use a terminal one, for example. There were two different reactions. These were hydration reactions, which you can still view in part as an oxidation, because I am adding oxygens as I'm doing this. But when we use the hydration reaction with a Markovnikov reagent, we use something like H3O plus and HgSO4. Basically, we used some source of Hg2 plus in order to do this. And the other option was we could do the BH3, right, the borohydride. This was the anti-Markovnikov version. And then we could do the peroxide and the minus OH. So go back and check out some of those videos if you don't remember this. This guy will give the following. So the Markovnikov, using the mercury ion, will give an OH here. And we're going to bring back some terminology here in a second. Okay, and then this one right here would give the following. This one would do the anti-Markovnikov, the less substituted position. And so this one would give this, right? So if you remember the name of these compounds, these are enols, referring to a double bond next to an alcohol. This structure right here is an enol. And one of the things that we know about enols is that they are going to very rapidly convert, oops, there's an L in there, rapidly convert almost 99.9% into the keto form. And hopefully you remember this or you came across this at some point. So what's going to end up happening is that these compounds above, I'm going to redraw them down here in their enol form. So this is for the Markovnikov addition. This enol, the all being the alcohol, the ene being the double bond, will readily interconvert into the keto form. And there was a fancy name we used for this, which is, these are called tautomers of one another. And so the hard word we always try to use is tautomerization, which is when these two are going back and forth between these forms. The tautomerization of this enol is really in favor of, so you could draw a very small arrow back this way, we're going to spend more than, so greater than 99% of our time in the keto form. Less than 1% of the time we'll be hanging out in the enol form. And so the same thing is true, even though we call it a keto form, the same thing is true of the anti-Markovnikov addition. That keto form is really an aldehyde in this case, but we are still looking at switching to the C double bond O formation when we do that. And so in this case, we head over this way, and the bulk of the product would really look like this, which would be an aldehyde. So again, creation of aldehydes and ketones. A lot of these reactions we learned beforehand. We learned them in Organic 1 or in the alcohol chapters at the beginning of Organic 2. So that pretty much sums up the main methods that we have come across. So oxidation of alcohols. Primaries can give aldehydes, secondaries can give ketones. If you're doing the primary, you got to stick with the Des-Martin or the PCC. The next one was the oxidation using ozonalysis to cleave apart alkenes. We have taken a look at the DIBAH reagent, the diisobutylaluminum hydride. And then we have also taken, that was for aldehydes, we've also taken a look at the alkynes and their addition of an alcohol to form an enol, which will readily convert into the keto or the aldehyde form. So that pretty much wraps up aldehyde and ketone formation. And the next set of reactions, we'll start looking at how to utilize how to utilize aldehydes and ketones. I'm thinking too far ahead because we can create alcohols out of them. So that is it for this lesson. Please remember to like, comment, and subscribe if this helped you. I'm happy to take questions in the comments section, and subscribing will be the fastest way that you get updates on material that I put out. Other than that, have a fantastic rest of the day, and I will see you guys for the next lesson. Take care.